Recall in Spark streaming, there are two kinds of things we can do to a D stream. There are transformations and output operations. Among transformations, those are divided into the stateless transformations and the stateful transformations. Here we're going to zoom in on the window transformations, a particular kind of stateful transformation that you can use to manipulate a D stream. Now, let me tell you how window transformations work. The idea is that you've got a discrete stream or a D stream coming in. We're going to apply a window transformation to it, and that is going to produce a new D stream as its output. What we're going to do is we're going to look at the batches. Remember that a D stream is composed of these little RDDs that are chiseled off out of the input stream every so many seconds. We're going to slide a window over those chunks of the D stream and aggregate those pieces into a new RDD in the new D stream. I think a little bit of an animation might help here. So you see our D stream coming in time. It's composed in the diagram of RDD1, RDD2, RDD3, and RDD4. And those just have zeros and ones in them, just some numbers in them that we're going to count. Then we're going to slide a window over that D stream like so. That window is going to slide. It's going to first encompass that first RDD, and there's an aggregation function here. We're counting the things in the window. We're counting the number of data elements, either ones or zeros, that we see in that RDD. So right now, the window's got one. If we slide that window over again, it'll have two pieces. And that new RDD, applying that count-by-window transformation, will count all of the RDD chunks it sees in its window. Now, in that case, that's RDD1 and RDD2. There are 6 things, a 1, a 0, a 1, and a 0. As we keep sliding that window forward, we'll keep counting. Now we see a 0, a 1, a 1, a 1, a 1, and a 0 in those two RDDs, and that is the new RDD we're outputting into the transformed D stream. Slide it along one more time, and we see it happen again. This time there are 4 data elements in RDD4 and 3 in RDD3, so we come up with a count of 7. So makes sense. Now, having seen that, let's talk about a couple parameters that we have to define when we're doing a window transformation. One is the window length or duration. That's the number of D stream pieces or discrete RDDs in the D stream that we're going to gather up in the transformation that we do. We'll consider, in this case, 2 at a time. The window sliding interval or sliding duration is how many discrete RDDs the window will slide along each time it's evaluated. In the case of our animation, you saw that that was 1. We moved 1 RDD along at a time. And each time we were considering 2 RDDs of the input stream. Now, how did we pick 2 and 1? Well, in this case, it worked out awfully nicely for the animation, and obviously that's always a key concern when you're trying to learn a technology like this. But in your case, you're going to have to think about a couple things. Now, D streams are formed by collecting streaming input for a certain amount of time, and so the window length in a window transformation is really manipulating that length of time. It's as if you're changing the grain, if you were to think of a time dimension in traditional analytics. And what should the grain be? In a sense, that's up to you. That's an engineering decision you have to make based on the kind of analysis you're trying to do. Now, a time base that is seconds or minutes long is reasonable. That's probably going to work well. Hours for a window length might not work so well. It's going to take a long time to compute. You're going to have a huge latency on updates to that D stream. And in the case of failure recovery, you've got lots more work to do. Lots more intermediate work has been persisted that you're going to have to recompute when you're recovering from a node failure. So if you've got a grain like that, and obviously hours, days, months, these are perfectly reasonable lengths of time to roll up numbers over. But if you're doing that, it's probably a better idea to discretize your transformed D stream on the basis of maybe minutes, and then have some other process that rolls those up to a larger grain of hours or days directly in a Cassandra table. So in other words, that roll-up kind of gets done outside of Spark streaming, and you're letting Spark streaming do roll-ups on the basis of minutes. There's very little general to say about the sliding interval. That really is going to be an application-specific thing where you're going to have to think through the kind of transformation you're doing, and often the sort of counting you're doing, or if you're applying some sort of reducing function, what's the nature of that reducing function, or really what's the computation you're doing. You need to understand how the sliding interval works, and then be able to make the decision about what it should be on your own. Be advised that a smaller interval will result in more computation. The more of a jump you can take through the input discrete stream, the less re-computation you're doing over the input RDD pieces. So keep that in mind, but in general, that's your decision to make. Let's take a look at a little bit of the API that lets us do these window transformations. Remember, these are functions that we're going to call on a D stream that are going to create a new D stream. Window is the simplest transformation. We give it a window length, which again tells us how many input discrete RDDs we're going to gather up into a new one in our output D stream. And the default slide interval is going to be the batch interval of the source D stream. In other words, we'll essentially slide along one input RDD at a time. CountByWindow is a way of counting up the number of elements we see in the input stream. Remember, the discrete RDDs in the input stream are sort of chiseled off on a time basis. We'll cut one every, say, 4 seconds or 5 seconds or something like that. And we don't know in general how many input elements, how many tweets, how many log entries, how many clicks on our website, whatever the thing is that we're streaming. We don't know how many of those will end up in each RDD in the batch. So countByWindow is a way of counting those things, and we give it explicitly a window length and a slide interval, and we get that count back. countByValueAndWindow is a lot like countByWindow, except we're counting discrete values. So these discrete RDD pieces in the input D stream have things in them, and this is going to look for uniqueness in those things and count the number of times unique things in the input happen in the window. So if, for example, the input D stream contained just numbers, then we'd get the number of times the number 5 occurred, the number of times the number 42 occurred. Any unique values in the input D stream, we're counting them uniquely. And of course, we can specify window length and slide interval as you'd expect. reduceByWindow is doing the same thing. It's gathering up input discrete RDDs and batching them according to the window length and the slide interval, but the batching is going to be done by applying a reducing function, and that's a function that we pass in. So if we are just getting, say, counts coming in, just raw numbers, then we could add them up, and the reducing function would then be addition. So the resulting D stream contains that sum of the values in the input D stream. Whatever that reducing function needs to be, we're able to pass that in, so it can be anything as long as it's an associative function. reduceByWindow has another interesting flavor where we pass it two functions. One is the reducing function, the other is the inverse reducing function. This is kind of cool. So imagine the window sliding along the RDDs on the input D stream, and we're doing some kind of reduce function. Say we're doing an average. Now, we could just do that. We could have a global average over all time of that input D stream. That's a valid window transformation. Imagine, though, if we wanted a moving average, then we'd want a way of, for each time an RDD falls off the edge of the world, we want to say, well, let's take off those values. So we have the reducing function, and we have the inverse reducing function that takes away the effect of that RDD that's falling out of the window. It's kind of a nifty thing, and the most obvious application off the top of your head is probably something like a moving average, although you can use it for anything that you have an inverse reducing function to play around with. And here are examples of counting by window and reducing by window with the inverse reducing function, that third example down there. You can see those API calls play out about the way you'd expect from looking at the documentation. That inverse reducing function is a little tricky. I was describing it, but just in case that didn't work, let's look at a picture of that and just kind of watch the animation happen the way we did before. So we're going to slide a window over the same 4 discrete RDDs, and we'll see things come in and go out by way of the reducing function and the inverse reducing function. So as that window slides along, the reducing function, in this case it's addition, adds up those 3 ones and gets a result, you can check my math, of 3. We move along, and now we've got a second RDD inside the window. We have 3 ones in this new RDD, and we add those to the previous state of the window, which, remember, was 3. So we get 6. Now we have to let an RDD drop off the edge of the world, so we have to use the inverse reducing function on that RDD to keep the window value honest. Now the fact that our inverse reducing function is subtraction is a consequence of the fact that our reducing function is addition. It's the thing that undoes the operation of our reducing function. So if we were doing a moving average instead of just a sum, of course you'd have to apply a different kind of function to eliminate the effect of RDD1 on that average as the window moves forward. And as we keep sliding along, we'll now sum up all the ones in RDD4 with the new previous window state. And we'll see we get a 7, and we'll subtract RDD2 from that summation. So that's kind of an animated version of that interesting way to do reduce by window. Now, if the DStream has key value pair data in it, in other words, if these are pair RDDs in the little discretized chunks inside the DStream, we've got a few API methods that treat those specially. There's reduceByKeyAndWindow. Same thing as reduceByWindow. We're sliding a window along, window length, slide interval, they mean exactly the same thing. And again, we have a reducing function that we pass in here that's going to do that reducing. It's just that the method will collect all of the values having the same key across the windowed batches and apply the reducing function to them. And of course, the output will still be a pair RDD, so we'll see those keys grouped together. reduceByKeyAndWindow also has the flavor where I pass it a reducing function and an inverse reducing function for the moving average case. And of course, I have a groupByKeyAndWindow method that's going to look for common keys in the RDDs across the windowed batch in the input DStream according to our window length and slide interval. And in the output RDD, the resulting RDD, all of the values of common keys will be collected together in the value of that pair RDD. So it works just like you'd expect a group by to work. Find all the things that have the same key and make a collection of those values in the output DStream. So if we wanted to do a reduceByKeyAndWindow over a 60-second window, that's a 1-minute window that moves along 4 seconds at a time. Now, 4 seconds here just happens also to be our batch interval when we defined the stream. That's not shown in the slide, but that's the batch interval we're working with in all of our DStream examples. This will slide along one discrete RDD at a time, but reduce a whole minute's worth at once. And the reduce operation, as you can see, is addition. We also show the reduceByKeyAndWindow with the inverse reducing function, the reducing function being addition, the inverse function being subtraction. So this is the code that would implement the animation we just saw on the slide a minute ago. Now, a quick note on checkpointing. Checkpointing does get its own treatment in a section all by itself, but it's important to point out that for most windowing operations, it is mandatory. What checkpointing will do is persist the Spark application metadata, and some of the data, some of the intermediate data, will be persisted to disk. It looks for, in this case, the Cassandra file system, or CFS, and it writes it into that. Now you enable checkpointing by calling the checkpoint method and passing it the directory where that stuff will get written, and then start your application and let the streaming go on. We will treat checkpointing separately, but you should know that it's required for your streaming application to work.